we started sequences and series, and we said that we are learning about two very basic special types of sequences that are called arithmetic and geometric. And we have been looking at these two and different aspects of these two sequences. And we started to talk about the series, the corresponding series of these sequences. So series means when you add the terms of your sequence. So you can add a finite number of terms or infinite number of terms. So we looked at, the last thing we talked about was finite series, how we can compute the sum of a finite number of terms in an arithmetic sequence. So that you call it a finite arithmetic series, and we learned the formula for it. And you can derive another version for this same formula by plugging in the UN formula here. So I haven't written it here, but we wrote it down last time. And then for a finite geometric series also, we have a formula that we can use to compute the sum of a finite number of terms in your geometric sequence. So what this means is that if you have a sequence, arithmetic or geometric, you don't have to sit and take a calculator and one by one add the terms. But if you have certain information, you can compute the sum of a certain number of terms by using these formulas, right? Um, Right. So today we have to do infinite series. What about if I want to add, if I have a, let's come to arithmetic first. If I have an arithmetic sequence that has no ending, that goes on forever, a simple one would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's an arithmetic sequence, isn't it? Each term increases by 1 each time. So you're adding a 1 each time. So the common difference is 1. So if you consider that sequence, which is arithmetic and which is infinite, can we talk about the infinite sum of all the terms? I mean, when I say all the terms, it has no ending, right? Is it possible? What can you say about that? So this is what we are going to learn today. So up to here you have done, I have just summarized it here. So your second bullet point under arithmetic series is infinite series. What about infinite series? I have an arithmetic sequence and I'm thinking of the possibility of adding all the terms. And when I say all, I mean all, but it's infinite, right? Is that even possible? So this is what we are thinking now. Infinite series. So we are going to look at the same thing for both types. Infinite series. You can write with me. Let's highlight infinite. Finite, no problem, right? We can all make sense of that. As long as you are adding up to some term. Can be, you are adding million terms, billion terms, trillion terms, doesn't matter how many, as long as you are stopping somewhere, your addition, you can compute it. But what if I just want to find everything? Is that possible? I mean, that's something intriguing to think about. So if I write a little diagram for it, what I mean is this: I can't even show it now. In your under finite series, I showed you. You start with U1, U2, U3, U4, up to UN. You're adding. But here, what I mean is, if I write the first term as A plus. So this I'm talking about in arithmetic, right? A plus U2 plus U3 plus U4 plus, I can't show you where I'm going to, if I put 3 dots, that means I am going to keep continuing adding this. Like, so I can't even draw that, the curly bracket and show it because it doesn't end. But what do you think about this? Do you think this is possible? Do you think this is possible? What do you think about this? Do you think we can have a formula? Do you think a mathematician would have been able to derive a formula for this? So the symbol is S infinity. So here Sn, right? Let me highlight that n. It's a certain number, finite. S10, S20, S million even, S trillion even, possible. What about S infinity? That infinity symbol only means, it's not a number, you know that, right? It only means you're going to add this continuously on and on and on and on without an end. Um, is that possible? What do you think? Can Senitu or Umasha say something? What do you think about this? So, and remember, arithmetic sequences, it goes by addition of a number. Your number can be a positive number, in which case the terms get bigger and bigger. If what you're adding is a negative number, your terms will get smaller and smaller. Yet, that now I think last time Senithu was saying, if the numbers get small and smaller, you can add them, but then still there are infinitely many terms. How small, however small they are going to be, you have to keep adding them. You can't say, oh, let's ignore after this. You can neglect because they're very small. They don't change the sum anymore, even if I add them. You can't do it. That's in math, we don't do that. So since you're not saying anything, for arithmetic sequences, infinite series don't give you, there is no formula. If your d is positive, that means your terms are getting bigger and bigger. When your d is positive, if you find s infinity, you get, give me a moment. You get your S infinity. Let me write S infinity in red. There is no formula. I mean, there is the answer of this sum is not going to be a finite number. So S infinity is going to be, for an arithmetic series, S infinity is going to be equal to, I will highlight infinity, I'm adding infinitely many terms. If your D is positive, this makes sense. If your D is positive, your terms get bigger and bigger and bigger. So your summation, if you keep adding them, you're not going to end up with a finite number. You're going to get as your answer infinity. I mean, and that again is, it's not a number, remember. It's even though I say you get infinity, it's not a number. It only means it keeps growing and growing and growing. You get infinity if your D is positive. And if you get what if D is negative? Can you tell me that? If your D is negative, your numbers are going to go into negative numbers from whichever number you start with. Even if you start with a positive number, if you keep adding a negative number means you subtract, then you go into negative. Your terms will eventually become negative, and from that point onwards, all the terms are going to be negative. And when you add them, infinitely of them, you're going to get what here? Senitu? Umasha? You can say what this is. You can say what you're going to get. Negative infinity. Very good. Negative infinity. That only means you will get a negative sum, and it keeps growing and growing and growing. That's what negative infinity means. It doesn't mean this is not a number. Remember that infinity is not a number. It's just an idea that it keeps growing. This keeps growing in the positive direction. This keeps growing in the negative direction. So you get a positive sum and it keeps growing. So you can't find an answer. If D is negative, your sum is negative and it keeps growing in the negative direction. Like negative 100, negative 200, negative 300. In the negative direction, it's a big number. That's it. I mean, so nothing. So this has no applications. I mean, you will not get any questions out of this. This is, in other words, it's not possible. I mean, there's nothing that you can do. You can't add all the terms of an arithmetic series. Copy that down. Okay. Did you copy with? Did you write with me? Can I start talking about geometric infinite series? So here also we have, I mean, let's write what this means. If you want to know, how do I, so this means infinity, just for your, this is for your knowledge. It only means, I will just say means increases without bound. Increases without bound. Sure, Masha, I'll give you 2 minutes. And then this means decreases without bound. Because a lot of the students have this misconception that infinity is a number on the real number line somewhere at the end. There is no end. It's just an abstract, it's an idea. It's a symbol to indicate, to denote an idea, the idea that it's growing. It goes on and on and on. That's how we say. This means if D is positive, the sum is positive and it increases and increases and increases. That's what this means. If D is negative, the sum is negative, and in the negative direction, it increases and increases. That means decrease. Negative number, when negative of the number, this, if this number increases due to the negative sign, it means it's getting smaller and smaller and smaller. I mean, not smaller. Small is not the word. In the negative side, right? You can say smaller. So in other words, I mean, this only means you can say S infinity. Thank you, Masha. Sorry. S infinity is not, not defined. You can't find. You can even say that. But this is what happens. Let's think of then geometric. What about geometric? Would it be any different? So again, we are thinking of, we now have a geometric sequence, and we want to add all the terms, u1 or a plus u2 plus u3 plus u4, and I go on and on and on. How do you say you go on and on and on till infinity? You put 3 dots. 3 dots. That means you go on and on and on without stopping. That's again a symbol. This is a symbol. Now we are used to putting dots when you write something. I'm so hungry. Dot 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 dot, like that when you message. This is a mathematical symbol. In math, when you put 3 dots, like you write something, and then you put 3 dots, it means this continues till infinity. That's the meaning. So this is an infinite series. Now, when it comes to geometric sequences, and when you want to add infinitely many terms of a geometric sequence, something interesting happens. If your common ratio R is a fraction, fraction can be a positive fraction or a negative fraction. I'm talking about proper fraction, a number less than 1, fraction, half, 1/3, 2/5, any fraction, negative or positive. So negative half, negative 1, sorry, not 1, less than 1. So negative 2/5, 3/5, 1/3, 1/4, 1/8, any fraction. If your R is a fraction, we can compute the sum to infinity. We say sum to infinity. Even though if you think of it as having to sit and keep adding these terms one by one, physically that's not possible. That's not what we are talking about here. We are not talking about the possibility for somebody to sit and, can you finish adding this? You can't finish adding it because it goes to infinity. You will die. You will have to keep adding until you die. And as I said last time, your son, your child will have to continue, your grandchild will never end. That's not what we're saying. But a formula can be formulated, and that you might think, how is that possible? it uses the idea, what is called the limit idea. I don't know whether you have heard of this. We don't have that in our syllabus. But using this powerful mathematical idea called finding the limit of something, you can find the infinite, the value of an infinite series for a geometric series when r is a fraction. That means when r is between 1 and -1, any fraction between 1 and -1, you can compute s infinity. That's amazing. Okay, so we'll write that and I will show you, I'll give you an intuitive idea how that is possible. Um, so first we'll write it. Okay, so write a little sentence here. Um, the sum of, should I write it too? The sum of infinitely many terms, infinitely many terms, within brackets s infinity of a geometric sequence can be computed, not always, can be computed if your r is between 1 and -1, less than 1, greater than -1. In brackets, you can say what that means is if r is a fraction, positive or negative fraction, if r is a fraction. And here's the formula. I will give you the formula and then I will explain how that is possible. Okay, so for a geometric sequence whose common ratio is between 1 and -1, if you want to find s infinity of that sequence, can be done, and you can use this formula. It is s infinity equals simple formula, a over 1 minus r. That's it. A over 1 minus r. You only have to know the starting term, the first term a, and the common ratio. If you have those two, and if r is between 1 and -1, again we'll write alongside this formula the condition for r. You can only do this if r is between 1 and -1. You only need to know the first term and r. And such a series that gives you a number answer for the sum is, we say that it's a convergent series. Because what happens is, as you add, if you think of actually physically adding the terms, if you keep adding them, the sum, you can see that the sum is going to settle on a certain number. You can see that it is converging. Your answer is converging towards a certain number, and that number is going to be your answer. So you can see that your sum is going there. However many terms you add, it keeps going to that number. So you can't finish adding this, but you know that's where you're going, kind of idea. This is what it is. Okay? So if this happens, we say that this series is a convergent series. A geometric series whose s infinity gives a finite number is called a convergent series. Convergent series. Convergent series. So a convergent series, so any geometric series, any geometric sequence with r between 1 and -1. Yeah, so we are not learning how this is derived, but I can show you, and I can't show you with the math that is available to you. I can't show the derivation of this anyway, but I can give you I can show you how it is possible. Let me show you. I will come to that. Okay, convergent series. So all these are all arithmetic series are what then? If you get for S infinity, if you get a particular number as the answer, we say that the series is convergent. If you don't get an answer and it keeps growing and growing and growing, we say that the series, they are divergent. They keep on growing and growing and growing and growing and growing and growing and growing. Divergent. Very good. So this is all divergent. And for geometric also, if r is greater than 1 or less than -1, they're all divergent. Only the geometric series whose r is between 1 and -1 are convergent. Okay, and I'll show you now an example. You can copy this if you think this is useful to you, but I'm not giving this as part of the note. I will do it here. Here's an example. This is just to convince you, okay? Because otherwise you will just be, oh, is that possible? So it's possible to do. Oh, okay. You will be just accepting what I'm saying, right? You're adding infinitely many terms, and that is possible to do. You get that with this formula. Ah, okay. Right? It would be like that. But here I'm going to convince you. Here's an example. So I'm writing it here. If you're going to write it down, you should write it in your column. But I'm going to just write it here. I'm going to show you an example for a geometric series with r between 1 and -1. Consider this one. Consider this sequence. 1, half, quarter, 1/8, dot, dot, dot. First, tell me, is this an arithmetic sequence or a geometric sequence? Geometric, very good. This is a geometric sequence. This is geometric. If it is geometric, what is its R? What is its R? Oh, very good, 0.5 or half, 0.5, or I can say half. 1 times half, half. Half times half, 1/4. 1/4 times half, 1/8. It gets halved each time. And it goes on forever. It's an infinite sequence. Now I'm going to consider adding all the terms of this sequence. So here's the S infinity. I'm going to write S infinity for this. It would mean I have to do 1 plus, half plus, quarter plus, 1/8 plus. There is no stopping. 3 dots. Okay. And I will show you now what I said here was, this summation has an answer. Right? I mean, that blows your mind when you think about it. How can it have an answer when you keep adding and it never ends? Here's how you prove it. I will show you a pictorial proof. Pictorial, okay? Geometric proof. I'm going to draw a diagram. I'm going to draw a picture for each term. Now, to represent one, I'm going to draw a square. Suppose this is my 1. This is the term 1. This represents the term 1. That's my 1. Okay. Now I have to add to this. I think this is a tile. Okay. A square tile. That's my 1 unit. And then I have to add, my second term is half a tile. I have to combine with this half a tile. So let me put it, where do I put it? Let me attach it here. So half of a tile, right? Half, like that. So to here. Half of a tile. There's my half. Now I have how much up to here if I add? If I add only 2 terms, 1.5. Then I add my third term, quarter. I have to add to this. So I have here 1.5 tiles. I have to add another quarter tile to this. So I'll keep combining, joining tile pieces to this. Okay. So I need to now join to this a quarter tile. So that means half of this piece. So this is half of this tile. Then half of that tile. I'll put it right here. So I'm doing it in a certain fashion. There's my 1/4. Okay, so 3 terms, if you actually add them, you get, so that's, you do it and see 1 plus half plus quarter is some answer. Okay, my next term, if I do my next term, that should be half of this. Half of this, if I do it like here, it would right fit in here like that, isn't it? So this is one line, and this would be quarter, I'm sorry, 1/8, correct? My next term would be, I haven't written it here, 1/16. That would be half of this tile. So actually, if I do it physically, like if you think of this as adding tiles, combining tiles, I have to chip half of it and put it and combine it. So half of this tile, if I fix it here, it would look like that. That would be 1/16. I don't even have enough space to write 1/16. That's 16. And then keep going now, okay? Half of that tile, put it here, half of that tile. Then half of that tile, put it here. 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 Half of that tile. If you keep doing this, zoom this picture out, zoom in, then you can nicely draw it. Do you see where you're going? If I keep doing this, would I ever exceed? It goes no further than 2. Are you convinced? It's converging towards 2. I can surely say that from this pattern, I would keep filling that little space here that is left now. That's all what I will be doing. I would keep filling that. Would I ever exceed 2? No, I would not exceed 2. And even if you keep doing it until your grandchild, generation to generation, the only thing you'd be doing is filling that little gap. The little space would get smaller and smaller, but you're still filling that. So it's going towards what? It's going to be 2 someday. There is no someday, but that's what it is. So this sum, you can surely say it's 2. And that's amazing. I mean, yeah, you can say it becomes 2. Who's going to sit and do and check? I mean, it's not possible, but that is 2. So this is the idea of limit, okay? Idea of limit. Anyway, we are not doing that. So if you actually use this formula for this sequence, what is A? This is your A. This is your R. Put it here and see whether you get 2. You do get 2 for that. You're asking, will it actually become 2? What does your gut feeling say? Like, if you think about this, it approaches to, that's why I say it's convergent. That's why we say it's convergent. So it should be 2. The sum should be 2. Right? What we mean is that this sum is approaching 2. So the sum should be 2. We know that it's not anything, it is not 2 point something. It can't exceed 2. It can't be less than 2 because it's filling this up. And if you do it infinitely, it's going to be 2. It's very, this is the fascination of mathematics. You're doing things that these don't happen in actual, right? You can't do it this is not practically possible, but this is a thought process that we are thinking. Thought experiment. Right. So hope that is clear. I just wanted to give you a little bit of that, the beauty of that, without just showing you the formula. Right. So with that, that's the end of sequences and series. We can try a couple of questions now, and we can start binomial theorem, right? Which is the other topic under this topic. Right, shall we try a couple of questions? I first want to, now I have the booklet, but I haven't given you the booklet yet. So do you both have your textbooks? Even if you don't have, I can show you the question here. Let me try. Can I keep the book here? Let me see. Do you see this number 17 and 18? So these two, okay? This is from your textbook. This is under, these are two questions, exam type questions under arithmetic progressions or arithmetic sequences and series. Shall we try those two? So you write exercise, and if you want to know where this is exercise 4A in your book. Exercise 4A. Okay, Umasha. Your book might not be the exact edition as mine, but just check exercise 4A, the last two questions. Check whether they are the same as what I have in my book. So let's try number 17 first, okay? So it says, the first term of an arithmetic progression, same thing. Okay, good, Umasha. So let's do it then. Number 17. The first term of an arithmetic progression is 6. So you can say A equals 6. Okay, that's what they have given. It's important that you write down the information given in symbolic form. So A is 6. A is equal to 6. And fifth term is 12. How do you write that? Fifth term is 12. How do you write that symbolically? U5 is equal to 12. You have U5. You have A and you have U5. Then the progression has n terms. It's finite. It has n terms. And the sum of all the terms, these n terms, Sn, is 90. Okay? Find the value of n. How many terms in the sequence, in other words? So that's the question. I hope you wrote down the information. Let me remove the book now and let us try it together. Let us try it together. So let me write down. So this is exercise 4A. Question number 17. Senitu, do you have the book too? A is 6. Right, okay, both of you have. A is 6. U5 is 12. I'm just writing down the information given to me. It has n terms and all the terms, so n terms are there. So A, U2, U3, and so on, and UN. There are n terms. Right? It's finite, n terms. It stops here. They have given the sum of all the terms. What is that? S, n. We don't know how many terms are there. Let that be n. Let there be n terms. This is the first term, second term, and so on. This is the nth term. Nth term. So Sn is 90. We are asked to find what n is. How many terms are there? What things can we do here? Now remember, we have a formula for the nth term. We have a U formula and we have an S formula. If you apply those two here, now it's an arithmetic sequence. We don't know D. D is not given. So D is an unknown here. And we don't know how many terms are there in the sequence as well. But since U5 and Sn are given, we can write formulas for these two. Shall we write the formula for U5? From this information, I'm going to apply it into my formula. U5 is equal to, I can say A plus 4D, is that right? U5 must be equal to A plus 4D. And I know U5 is 12. I can plug in 12 here. I know it is 12. I know what A is, 6 plus 4D. I can find D from that. I can find D from that. So how much is D? 4D is 6. So D is 3 halves. Sorry, yeah, right? See, I started with that information and applying it in the formula, I was able to find D. Now, I'm sure that would help me to find N. Now, here's the second information given to me, Sn, which I can use in that formula. What's the Sn formula? Let me write it first. Sn formula is N over 2. I'll use the one with D in it because I found D here. 2A plus N minus 1 times D. Right? Let's use that. So I know what Sn is. Sn is 90. I don't know N yet. I know what A is. 2 times 6, 12, plus N minus 1 times 3 halves. Now this equation only has the unknown N. That means I can solve this to find N. Can you solve it? I will give you time. Is my D right? Did I do the D correctly? I think so. Oh, you get a quadratic equation, isn't it? Now you may be doing in a different. You don't have to copy my steps. The simplification of these brackets and all can be done in different ways. You do it the way it doesn't matter, right? I usually like whenever I have fractions, I get rid of the fractions by multiplying by the common denominator, because then I get a line without any fractions. That's easy to think about. So it's a quadratic. Have I made a mistake? Is this what you get? Oh, there's a 4 here. Oops. Oh, no, there is one 4 there. I multiply by 4 now. I think it's right. Okay. What are the two factors here, Sinitu? Does this factorize nicely? 8 and 15. So it's plus 15 minus 8. And you get n equals minus 15 or n equals 8. You reject this because the term number can't be minus 15. So that's the answer you keep. So there are 8 terms. Correct, now? Umasha, did you get it too? Okay, no problem. Let's wait till Umasha finishes. Now, this is something I want. Okay, Senator has a question. Miss, without going for common denominator, could we at first get rid of the 2? Get rid of the 2 means without going for common. You mean, yeah. Yes, here, right? Yes, you can do that too. The reason why I removed the bracket was because here also I had a fraction. So to see, so I know that I'm going to get a different denominator. So if you get, yes, you can get rid of the 2. I told you, right? I mean, the way you would have done your simplification or the manipulation of these terms could be different. But we will all arrive at this. That's for sure. We will all have to arrive at that. But what happens in between could differ depending on what you do. I mean, it depends on the way we are used to, there are certain ways now. As long as your steps are right, we will all get that. And as long as your steps are right, you can simplify these manipulations. You can do anything, in any order you want, in any way you want, doesn't matter. There are no fixed, you have to first do this, and then you have to do this next. There's nothing like that. And what I was going to say was, when Umasha said that she's still doing, in math, how long you take to do a sum has nothing to do with your ability. Oh, wow. When did I get stuck? What happened? Is the recording still going? It is, right? Is it? Ah, recording is still going, right? Yeah, so I was just saying that how fast you do your questions, don't worry about that. Take your time, okay? Umasha, are you done? So just let me know when you're done. It's okay. It doesn't matter how long you take to do something in math. I always say this, the speed is only a requirement. Okay, Masha, the speed is only a requirement for the exam because we are sitting for exams. In math, it doesn't matter how long you take to do something, to work on a problem. Right, shall we look at number 18 now? Since you all have it, let us read it together so I don't have to put it under the screen. The first term of an arithmetic so as we read, I'm going to write down start working on it. So this is number 18, same exercise. The first term of an arithmetic progression is 61. A is 61. And the second term is 57. Second term, okay, I can just write the sequence then, 61, 57. Or you can say U2 is 57. I can immediately write what D is. D is 57 minus 61. That is how much? Minus 4, right? Then the sum of the first n terms, okay, again. So they're talking about the sum of n terms, up to un. up to un. Okay, Sn, they're talking about that, Sn. Sn is equal to n, they say. The term position, say this is the 15th term, then S15 is 15. That's what they're saying, right? Find the value of the positive integer. Again, what is n? Would you like to try it on your own? What can we do here? So Sn is what is given to us. We can apply the Sn formula. I have A, I have D. Okay, let me put Sn formula. Sn is n over 2, 2a plus n minus 1 times d. Sn is n, right? Sn is n. N divided by 2, 2a, 2 times 61 plus n minus 1 times minus 4. Huh, nice. You have an equation with one unknown n. You can solve it to find n. Oh, and I can cancel this off, isn't it? When you do that, you have to say, I'm doing that because it's not equal to 0. You can't cancel. Canceling something off means you are dividing both sides by n. You can only do that because it's not equal to 0. If it is 0, you can't divide by that. So this is actually 1, so it's 2. Is it 30? Oh no, it's not 24. 31. You got this? Okay. Umasha? I'll wait for Umasha. Okay, great. That was not bad, right? How did you find those two questions? They were okay, isn't it? Right, let's look at the next exercise, 4b. In exercise 4b, so you can find it in your books, 4b, I want you to start with number 18. These are exam questions. I'm only picking, okay, Amasha, same answer. Good. So let's look at 4b number 18. And let's see whether we both have the same questions. Do you have a question with part A and part B for number 18? So in part A, let's read it and do. Question number 18, part A. The first and last terms of an arithmetic progression are 12 and 48 respectively. First and last term. So let's say so first term is A is 12. And so this is a sequence that goes like that, UA, U2, U3. So there is a last term. Let's call it UN somewhere, the last term. Let's call it the nth term. We don't know what n there is. Can be 20 terms, 20th term. So let's say the last term is UN. Then UN they have given is 48. And UN is the last term. Okay? UN is the last term. The sum of the first four terms, up to four terms, S4, they are talking about S4. S4 is 57. Find the number of terms in the progression. N. Again, here are the two things to which we can apply formulas. We have a UN given 48. We can apply the UN formula for that. We have an S given. We can apply a formula for that. Let's do for this first. So UN we know is A plus N minus 1 times D. This is 48. A is 12. We don't know D. We don't know D. Let's keep it like that. So, okay. So I have gotten an equation with two unknowns, N and D. So let me just call it one. For sure, I have to set up another equation with N and D. Then if I have two equations with the same two unknowns, I can solve them simultaneously and find them. So maybe I can get another equation with in terms of N and D using this. Let's use the Sn formula. Sn formula is N over 2, 2a plus N minus 1. Oh, actually, oh, I could have, do you see something? I could have straight away used, did you see that? The way I'm going to do also can do, and I'm using the Sn formula in which you have N and D. Remember, we have two Sn formulas. It's the same thing, but two versions. If you use the, let me do it on the side here. If I do this Sn formula, N over 2, A plus UN, because I have both A and the last term. I have both the first and the last term. This is S4. Can't. I'm sorry. That's not Sn. This is only the sum until the fourth term, not sum of all the n terms. So what I was going to do can't do. Okay. So this is what you should do. So n minus 1 times d. Sorry, I took you to a different direction. I have S4, right? S4. So if this is 4, this would be 4. This would be 3. I mean, yeah, this would be then 3. Let me write it properly. So S4 is 57. 57 would be 4 divided by 2. 2 times 12 plus 3d. I can find d from that. Do you see that equation only has d in it? Now, I applied this first. I can't do anything with that because I have two unknowns there. So I kept it just aside. And then I went on to the next information given and I applied the Sn formula for that. And then there I get an equation only with the unknown d. So I can solve it to find d. 57 is equal to is t 3/2. And then if I put it in, if I substitute it in the first equation, I can find n. Can you verify whether that is correct, what I've done so far? Okay. So yeah, that's 1.5, same as saying 1.5. Then you can use it in question. I will do it in a little box here. Sub d equals 1.5 in 1. Multiplying by 2. Is it 39? See whether it is 39. It's quite windy here. You're still doing? After finding D, it's only a little bit off now. Is it not? $39, right? 72. 75? Yes, Anita. Marsha, looks like we both have done a mistake. 3n, so this is 24 minus 3, 21. 96 minus 21. This is wrong. Thank you, Senator. 75. And then this is 25. You're correct, Senator. Isn't it, Marsha? Yeah, okay. So n is 25. Okay. Let's do one more in exercise 4b. No, there is a part B. So that's part A. Let's do part B in 18. Same question, part B. The third term of a geometric progression is 4 times the first term. The third term, U3, is 4 times the first term. 4 times A. Right? That's how you would write that information in symbols. U3 is 4 times the first term. Third term is 4 times the first term. U3 is 4 times A. The sum of the first 6 terms is the sum of the first 6 terms. That means S6, right? Sum of the first 6 terms is K times the first term. K A. Is that right? K times K some number. K times the first term. Find the possible values for K. Find the possible values for K. Possible values. That means there are more than one value that K can be. Shall we apply again? We have only 2 formulas, UN and Sn. If they are not talking about S infinity, these are the only 2, the nth term formula and sum of n terms formula, Sn formula. So if we use the UN formula, let me write it. So I want to write it for U3. U3 would be, this is geometric, A R squared. Is that right? AR squared to U3. U3 is AR to the power of 1 less than this number. So R squared. Then I know that U3 is 4A. 4A is equal to AR squared. I can divide both sides by A, but then for that, A must not be equal to 0. Remember, can you be certain that the first term of this geometric sequence is not 0? The first term of a geometric sequence, if it is 0, you're not going to get anything as a sequence. 0 times whatever is 0. So a geometric sequence can't start with 0. There's no point, right? So we are sure that the first term is not 0, so you can cancel it off. Then R is what? R is square root of 4. So there are 2 possible values for R. R could be 2 or R could be minus 2. Isn't it? For R, we get 2 possible values. Then, if we use the second information and apply the Sn formula, Sn formula goes, this is Sn formula for geometric now. What's a geometric formula? Sn formula? A 1 minus R to the power of n divided by 1 minus R. So we can apply this when R is 2 and when R is minus 2, right? So there are, because we have 2 R values, when R is 2, when R is minus 2, we can apply it. So let's do S6. We are doing S6. S6 is equal to we don't know A 1 minus R is 2 to the power of 6 divided by 1 minus 2. S6 I know is K times A. Oops, I'm sorry. You're not seeing what I'm writing. So S6 is KA, A times 1 minus, I'll work this out later, 2 to the power of 6 divided by 1 minus 2 is minus 1. And again, I can cancel off the A because I know A is not negative 0. I can solve this to find K, isn't it? Minus K, if I multiply both sides by minus 1. What is 2 to the power of 6? 2, 4, 8, 16, 32, 64. K is 63.
then if I do the same thing when r is -2, S6 is a times 1 minus 2 to the power. Now see, we didn't need the value of a. A gets cancelled off because both U3 and S6 are given in terms of A. That is strategically done by them. We didn't have to find A to do any of this. A nicely got cancelled off out of our equations. We didn't need it. So that's why I'm keeping A as it is. I don't know A and I don't mind not knowing A because I know when I substitute what S6 is here, I can cancel off the A. So 1 minus 2, again, power of 6 divided by 1 minus 2. This is Ka. Not 2. So when R is -2, this would be plus and this would be plus. Senithu, 1 plus 2? Yeah, so yes. Thank you, Senithu. Yeah, I had written 1 minus 2 because when R is -2, I'm doing this. Oh, wait. I have written this wrong here. This is wrong. Let me correct it. Now, I just changed my minus to plus. I can't do that. That's not how I should correct it. Wait. Now, the formula is 1 minus, but then the way I wrote it is, it's 1 minus, and then -2 to the power of 6. 1 minus r to the power of n. Now my r is -2. I can't bring this minus sign here. It's 1 minus. I have to first take the power of that number. Okay, so it's 1 minus. This is how it becomes 1 minus. What is -2 to the power of 6? 64 plus 64. So it's 1 minus 64 still. Okay, so it's not 65. And this is 3, right? 1 minus r is 1. Let me write how, this is right too, but let me write, it is 1 minus -2. That's how it is 1 plus 2. It becomes 1 plus 2. So 3. So 3k is 1 minus 64 is -63. And k is -21. I got 2 values for k. If r is 2, k would be 63. If r is -2, k would be -21. See whether this is clear? Now this was a good place where you can make a mistake very easily. Be very careful. You are plugging -2 into r. Don't mess with this outside minus sign. It's 1 minus, and it's for r that you put -2. So you should put it in a bracket. -2 to the power of 6. And because this power is an even power, you got plus 64 there. So it's 1 minus 64. Was that clear? Okay, so both of you got that, right? Nice. So I will assign you the next couple of questions for homework, and then we'll start binomial theorem now. Okay, so homework is in that same exercise, exercise 4b, question number 19. Can I give you up to 23? Do you all have that in your books too? 19 to 23, the same question as I have? Okay, so 19 to 23 homework. Okay, this is the homework. And we will start binomial theorem. So you can turn to a new page. This is the other topic under this, the section topic is sequences and series. But that part is over and you have this, what is called binomial theorem under this topic, because it has something to do with a pattern, like a sequence. Okay. Right. So on a new page, put your topic. We're still under this same topic. This also comes under sequences and series, called binomial theorem. Is this too? Oops. Okay. Binomial theorem. It's like Pythagoras theorem. It's a theorem. Okay. Before we start binomial theorem, we have to first learn a certain operation that you need to know that gets applied in this theorem. We need to know this operation. An operation means something like addition, subtraction, multiplication, division. Another new operation that you have not come across before. You have to know that operation because it is there in this theorem. You have to know that operation to apply this theorem. So we first learn this operation called the factorial. So I usually put this, I ask students to write this in a little box. It's a little note. So you need about 1, 2, 3, 4, 5, 6, 7, 8, about 8 lines. Let's write it and then later you can box it. Okay. Let's write a new operation. A new operation. It's an operation like addition. The name of the operation is factorial. Factorial. And the symbol for factorial is like for addition, it's plus, exclamation mark. Sometimes students say it's the Budu Ammu mark. Budu Ammu. Like, you know, right? When you factorial. Now, this operation is, we say it's a unary operation. Now you don't have to know this. I'm just saying it. Now, all the operations you have learned so far, like like addition, subtract. Let's think about the 4 basic operations: plus, minus, multiply, divide. These 4 operations have to be done with 2 numbers, isn't it? You need 2 numbers to add. You need 2 numbers to minus. Can you add with 1? That doesn't even make sense. To multiply, you need 2 numbers. Divide, you divide a number by another number. You need 2. So those operations are called binary operations. Binary means you need 2 things to add, 2 things. But factorial is a unary operation, which means it can be done on 1 number. It's like square root. Square root is an operation. It's a unary operation. You take a number and square root. You don't need, it's not something you do with 2 numbers. It's something that you do to a single number, right? So factorial is also a unary operation. We can talk about the factorial of a number. That's it. Factorial of 5, factorial of 10, It's one number. So what factorial means is very easy. I'm sure you may have done this if you are doing statistics in school. You may have, but if you have done this lesson itself in school, you have already come across it. Let's write what it is. I'll first give you a sentence. Okay, the factorial of and factorial. This operation is only defined for whole numbers. Only for whole numbers. You can't say factorial of half. That makes no sense. Factorial of 5, that makes sense. Factorial is defined only for whole numbers, and you will see why that is when you see what it means. So, right, the factorial of a whole number, the factorial of a whole number is, the factorial of a whole number is the product of the factorial of a whole number is the product of all the whole numbers starting from that number down to 1. Starting from that number down to 1. The factorial of a whole number is the product of all the whole numbers starting from that number down to 1. So example, if you have 6 factorial, you read it 6 factorial, and this is how you write it. It means you start with 6 and keep multiplying. 6 times 5 times 4, it's a countdown. 6 times 4, it's a product countdown, something like that. 6 times 5 times 4 times 3 times 2 times 1. That's what 6 factorial is. How much is that? How much? So in your calculator, there is a factorial button. So you can just do 6 factorial using the calculator. How much is this? $720. Okay. Can you do 4 factorial? It would be 4 times 3 times 2 times 1. 24. Right? So that's what factorial is. And remember, it's only defined for whole numbers. 10 factorial, 20 factorial, 20.5 factorial, nothing like that. Okay? No decimals, whole numbers, and only positive. No negative factorial. You can't say, what is negative 3 factorial? That's nothing like that. By definition, that's how we have defined this operation to be like that. And then 0, what do you think 0 factorial is? Again, according to, now we said you start with that number and count down to 1. Then what does 0 factorial mean? So it doesn't, it's not covered in that definition. So we separately define, by definition, 0 factorial is equal to 1. We define it like that. Okay? We say 0 factorial is 1. 1 factorial is also 1. 2 factorial is 2 times 1, 2. 3 factorial is 3 times 2 times 1, 6, and so on. 0 factorial is defined to be 1. Right, so let's close this box. You just need that factorial sign to learn binomial theorem. Okay. So this binomial theorem is a theorem that tells you how to expand a power of a binomial. Now you have to know what a binomial is and what do you mean by expand, right? So let's first look at the term. Let's understand this term by subtopic, binomial expansion. because the binomial theorem tells you how to do a binomial expansion. So you have to know what a binomial expansion is. Subtopic, binomial expansion. So if you focus on the word binomial, some similar terms you may have heard before are polynomial. Nomial means terms. Okay, so this word is bi plus nomial, right? Nomial means terms. Bi means two. So a binomial is an expression of two terms, like x plus y, two terms. So when you say terms, you know that terms in an expression, terms are separated by pluses and minuses. So you can have 3 minus x is a binomial. 4x plus 2y is a binomial. 3x squared plus 3x squared minus 10 is a binomial. Two terms. Okay, let's write that quickly. A binomial is an algebraic expression. A binomial is an algebraic expression of two terms. Two terms, write in red. A binomial is an algebraic expression of two terms. Example, I will write about 3 examples. I want you to add one of your own examples. 2x plus 3 is a binomial. X squared minus y is a binomial. Two terms, that's it, two terms, right? Can you add one of your own? You don't have to stick to x and y, like a, b. Put any variable letter, it's okay. But the two terms must be, I mean, if you write x plus 2x, now for example, if I do x plus 2x, one might say, oh, that is a binomial, but another one can argue, but that is just 3x, right? So it's true, this is 3x, and then it's a monomial, one term, monomial, but it can be broken down into a binomial. That's fine. So this could be thought of as a binomial too. We don't say anything about whether the two terms can be simplified further or not. If you have written two terms, it's a binomial, right? If you simplify that to one term, if you can do it, it becomes a monomial, right? So what is a binomial expansion? When you want to take a power of a binomial. For example, if I want to take 2x plus 3, I take this binomial and I want to raise it to the power of 4, or say power 2, or whatever. Let's take the simple ones. Let's say power 3. Okay. When I want to take a power of a binomial, that means I would have to, now if the power is a positive integer like this, if it is a whole number like 3, I know what this means. This means 2x plus 3 times 2x plus 3 times 2x plus 3. I have to multiply 3 of them together. And can I expand it? That's what expansion is. So you can expand it, right? You know how to expand 2 of them. So you would multiply these and then that with that. So you will get a long expression. That's called an expansion. It's called a binomial expansion. So what a binomial expansion is, when you have a power of a binomial and you actually go and expand it, you get the binomial expansion. Okay, so let's write that. A binomial expansion is a binomial expansion is when we expand the brackets, of a power of a binomial, of a power of a binomial. When we expand the brackets of a power of a binomial. Example, say x plus 3 cube. Okay, this means you would do, this means you have to do x plus 3 times, x plus 3 times, x plus 3, and say you expand it in full. This is what you call binomial expansion. Right? You can actually do it if you want and see. So that you find all the terms and you lay them down. That is called binomial expansion. And this is where the binomial theorem comes. Okay. This binomial theorem. Now, if I want to do x plus 3 to the power of 3, you would have to multiply 3 x plus 3's. And this can be done manually. If you know how to remove two brackets, then you just keep doing it continuously to whatever number brackets you have. Like you can do this, first you do these two, you get an answer to that, and then that times x plus 3. So you can manually, it'll take a long time, but you can do it manually, right? But suppose you have to do x plus 3 to the power of 10. Are you going to sit and do that? X plus 3 times, x plus 3 times, x plus 3 times, x plus 3. It's not practical. Binomial theorem tells you how to, just like that, how you can write the binomial expansion straight away without having to manually expand it. Okay, so that's what the binomial theorem is all about. So let's write that. Binomial theorem tells us, it's under, so after this example, oops, did I get stuck? Okay, so after this example, yeah, you write one sentence. Binomial theorem tells us a pattern to expand. Binomial theorem tells us a pattern to expand any whole number power. Any whole number power. We are talking about whole number powers, 3, 5, not power half or not power of -2, only whole number powers, okay? Binomial theorem tells us a pattern to expand any whole number power of a binomial,
Sometimes my screen gets stuck, isn't it, a little bit? Can I give me a moment? I'll bring some water. No, only positive. Whole, what are whole numbers? When I say whole numbers, 0, 1, 2, 3, 4, counting numbers with 0. 0 and the counting numbers. Okay, so this theorem that we are going to learn now only applies if your power is a whole number, not negative. This theorem, now there is another version of this theorem that can be applied to negative powers or even fractional powers. You learn that in P3, but this basic theorem that you are learning now only applies when the power number is a whole number. You will not you will not be able to apply this theorem if the power is, for example, -3, -4, or a fraction. Right? Only for this theorem is only when the power is a whole number. 0, 1, 2, 3, Even if the power is 100 can do. It's a whole number. But if the power is either a negative number or a fraction, then there is a different version of the binomial theorem, which is called the general binomial theorem, which you learn in P3. Okay, so put your next topic, binomial theorem. Now, the way I do this is, I'm not going to give you the binomial theorem on a platter. Here it is. I'm not going to do that. We are going to kind of discover it ourselves, not in full, but just to show that you could have done it, right? Somebody else has already done it. Some mathematician has done it. But I mean, we could have done it too. So, and also when you see this, it's easier to remember the binomial theorem. Okay, so I am going to make you do something now. Okay, consider. So I'm going to take a binomial, not a specific one, a general. Like consider the binomial a plus b. My a could be any term, my b could be any term. So actually this a and b I'm using to represent anything. My a could be 2x, my b could be 3y squared. Okay, so the symbol a I'm using to represent the first term, and the letter b I'm using to represent the second term in your binomial. This a and b can be any two terms. Okay, so we are doing this in general. So we are going to see whether we can identify some pattern going on here, and whether we can derive this on our own. So consider the binomial a and b, and let's take different whole number powers of a plus b. Let's take different whole number powers. Very important, whole number powers of a plus b. So let me write a few. You have to write this very nicely. Make sure that you have some space here. I want you to write a plus b to the power of 0 equals a plus b to the power of 1 equals a plus b to the power of 2 equals a plus b to the power of 3 equals, let's do till about power 5 to the power of 4 equals a plus b to the power. Did you do this exercise in school? Did you do this exercise in school? Did you do something like this in school? You must have done. Now don't start writing anything here. Tell me, did you do this in school? Not the Pascal triangle. This has a connection to the Pascal triangle. Did you actually expand this in school, like different powers of a binomial? Pascal triangle is the triangle with the binomial coefficients, right? Okay, now I want you to start filling this like this. Like I want you to get it like a triangle. Why do we expect a triangle? Now just think about it. What's a plus b to the power of 0? We know that anything to the power of 0 is 1. So this expansion has how many terms? This first expansion has how many terms when you expand it? It is just 1. So how many terms there? 1 term. So that one I want you to write right in the middle here. And then this expansion, when the power is 1, anything to the power of 1 is that thing itself. So a plus b to the power of 1 is a plus b. And how many terms there? 1. A plus b, how many terms? 2, a and b. Terms are separated by pluses and minuses. Okay. So the second expansion here, this one has 2 terms. So what keeps happening here is, as you increase the power number, the number of terms in your expansion grows. When the power is 0, 1 term. When the power is 1, you have 2 terms. When the power is 2, from experience, you know you will get 3 terms. 4 terms, 5 terms, 6 terms. So the number of terms get increased by 1 each time. So I wanted to place them like in a triangle. You understand? And then I also wanted to use different colors for the A terms and B terms. Okay, I will, shall we start writing it? For this, I'm going to write it A. I'm going to write A. So the any number I will write in red. So this is 1. So 1 in red. That is supposed to be red. Then A. I wish I had another. It's okay. A plus B. No. I mean, if you just have A plus B, the expression A plus B, if A plus B and is an expression, it has 2 terms, A, B. If you have AB, A times B, that is 1 term. AB is 1 term. A plus B is the sum of 2 terms. I mean, you can consider it as 1 term. You can put a, like you have done, put a bracket and say, I'm considering. You use the word consider, right? It has 2 terms, but let's consider by putting a bracket. Let's think of it as 1 term. It's like saying, I am one person, um, uh, and like in a family, if there are 3 people, I mean, this is a person, another person, and another person, 3 persons. If a family has 3 persons, you can like group them and say, let's consider that this family unit is 1 person. It's like saying that, what you're saying here. Or even now a family is a unit, right? This is a family, in neighboring house there's another family, and then you take the whole village and you say we are one big family. It's like saying that there are actually a lot of families there, but you say it is one family. It's like that. So you're considering this to be a term, but it has 2 terms. It is a binomial. In the name it's there, it's 2 terms. Right, so a plus b squared, for any a, so I will write, you get a squared plus, I mean, you have to use different colors here. I don't have enough colors. Then you will have 2 a b. The numbers I have to write in red. I forgot that. 2 a b plus b squared. Right? A plus b cube would be, I actually wanted to do it, expand and find it. You will see if you do it, you get a cube plus 3 a squared b plus 3 a b squared plus b cube. I'm actually filling this for you. If you do this, if you actually expand it, take your time and expand it, you will get, for that you will get, I don't know whether you already start seeing a pattern, a to the power of 4 plus 4 times a cube b plus 6 a, oops, wrong color. I write a in black and b in blue. A squared b squared plus 4. Now the coefficient of these terms is just 1, right? Let me place that 1. So all the coefficients here, I'm 1 a cube means 1 a cube. This is 1 b cube, 1 a 4. So 4 a b cube plus b to the power of 4, and this is 1. Now see, the only reason that I started placing these like in a triangle is because when the terms keep growing by 1 each time, if I place it like centered, I get a triangular shape. And then this last one, power 5, starts off a to the power of 5 plus, so this is 1, 5 a to the power of 4 b plus 10 a to the power of 3. Now you try to identify some pattern going on here. Plus 10 a to the power of 4 b cube plus 5 a to the power of 5 4 3. Oh, sorry, this is 2 a b to the power of 4 plus b to the power of 5, and that would be coefficient 1. I have written all the coefficients of these terms in red. I hope you wrote it with me. Now tell me things that you notice in this. Do you see any patterns going on here? We are trying to derive the binomial theorem. Now, what does the binomial theorem tell you? It tells you how to do a whole number power of a binomial, how to get the expansion, how to write this straight away. Now, like I did right now. Did I expand it actually? Or did I write all the brackets and manually expand it? No, I wrote the expansion straight away. What things do you notice in this? The first thing is, let's say, Seneca says horizontally, power of A decrease simultaneously with power of B increase. Umasha, see whether that is true. Now, when the power of Okay, so here power of a must be 1, right? I'm going to put the power of a. Just a means power of a 1. Now even here it's 1. Even here it's 1. When it's just that term, it's 1. And then here the power of b is 1. This is 1. This is 1 here. This is 1 here. This is 1 here. Yeah. Okay. Now, if I let me do a little highlighting. How the power of a. Now here only one a term. Here power of a. Okay. I'm highlighting power of a. 5, 4, 3, 2, 1. You actually have a to the power of 0 here. And let me highlight the power of b in a different color. And you will see what Senithu is saying is true. Good color other than, I don't know whether how good green will be. It's 1 here. Oops, it looks the same to you, right? Let me use this. Is that okay? Yeah. 1, 2. 1, 2, 3. Do you see that? I'm highlighting powers of b along any expansion. B 1, 2, 3, 4. 1, 2, 3, 4, 5. In any expansion, the power of one term keeps increasing, the power of the other one keeps decreasing. They go this way in opposite directions. Count down, count up. What else do you notice? So you also have to, with me like I did, highlight these things, okay? What else do you notice? What about these numbers, the coefficients? Where did they? Is there a way to get these now? These numbers in red. 1 and 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. What about those numbers? They are the coefficients, aren't they? Coefficients of these terms. They come from, if you have heard of the Pascal's triangle, like Senithu earlier said, another thing Senithu is saying is, horizontally addition of two numbers is the number below it. That's what, very good, Senithu. This is what the Pascal triangle is. Umasha, did you notice that? This one and this one, if you add these two, you get this 2. 1 plus 1 is 2. Let me write this. Let me write these coefficients that I highlighted in blue in a different. Only those numbers. Let me write like a triangle. On top I had 1, and then 1, 1, and then so 1, 1. Then 1, 2, 1, 1, 2, 1. Then 1, 3, 3, 1, 1, 3, 3, 1. 1, 4, 6, 4, 1, 1. Sorry, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Do you see what goes on here? This is called the Pascal's triangle. This is the sum of these two. This is the sum of these two. This is the sum of these two. 4 is the sum of 1 and 3. 6 is the sum of 3 and 3. Any number in this triangle is the sum of the two numbers on top of it, on either side of it. 5 is a sum of 10 is a sum of 4 and 6. Again the same. Like that it goes. And the edges are all ones. Okay. So there is a separate pattern going on in the coefficients of these expansions. And Senethu pointed out how the powers go like in opposite direction. This starts with the highest power, goes down. The other term starts with the lowest power and goes up. One more thing to notice. If you take any one term in any of these expansions, any one term, like take a random term. Now, do you know when I say term, what a term is? Here's a term. That's one term in that expansion. Here's another term. 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 So this last expansion has 6 terms. 1, 2, 3, 4, 5, 6. If the power is 5, you will have 6 terms. If the power is 4, you will have 1, 2, 3, 4, 5 terms. Sorry, yes, 5 terms. Always the power that you have one more than the power number, many terms in your expansion. And if you check any term, you have the powers of A and B. Add the powers of A and B. What number do you get? Here only A. If you had a B, the power of B is 0, isn't it? There is no B here means if you impose a B here, it would be B to the power of 0. So the two powers add up to 5. These two add up to 5. These two add up to 5. 2 and 3 add up to 5. 1 and 4 add up to 5. 5 and 0 add up to 5, which is the power number. In any term, look at a different term in a different expansion. 3 and 1 is 4. 3 and 1 is 4. This is 4. This is power 3. So 3, 2 and 1, 3, 2, 1 and 2, 3, 3. You saw all that? Now, if just by thinking of these patterns that we saw, let's try to do, you have to do, okay? Let's try to do A plus B to the power of 6. Let's try to write this. You tell me how I should start. First thing, let's find out the coefficients of the terms using the Pascal's triangle. Now, this is for power 0. This is for power 1. This is for power 2. This is for power 3, power 4, power 5. Let's build the next row in this triangle. What do we get? You know, you have to start with a 1. The two edges would be 1 and 1. This is 5 and 1, 5 and 1, 6, 5 and 10, 15, 10 and 10, 20, 10 and 5, 15, 5 and 1, 6 and 1. So the coefficients must be 1, 6, 15, 20, 15, 6, 1. Each coefficient corresponds to a term. There must be 6 coefficients, 1, 2, 3, 4, 5, 6, sorry, 7 coefficients. If the power is 6, we expect 7 terms in our expansion. So let me fill out these coefficients. First term 1, like I can first of all, I can separate out how many terms I have to expect. 7 terms. So if I leave spaces and put pluses, 1, 2, 3, 4, 5, 6, 7, okay? And the coefficients are 1, 6, 15, 20, 15, 6, 1. Then let's do the powers of A to the power of 6, A to the power of 5, A to the power of 4. I hope you are doing this with me. A to the power of 3, A to the power of 2, A to the power of 1, A to the power of 0. Let's write it. A to the power of 0 means just, that's nothing, 1. That's just 1 again. And then if you fill out the powers of B, you start with B to the power of 0, B to the power of 1, B to the power of 2, B to the power of 3, B to the power of 4, b to the power of 5, and b to the power of 6. You wrote the expansion. Did you understand that? Senitu and Umasha. Okay? Did you understand that? Oh, Umasha. Okay, where exactly? Like, did you see the pattern that went on here? No problem, Umasha. Let's talk about it again. Okay. Did you see the pattern when I was like different patterns I was pointing out? First thing is this. You understood all that? Okay. Okay. So a number of different points we pointed out. First was that these coefficients, you know what coefficients are, right? Did you understand that part? How these coefficients match with the numbers in the Pascal's triangle? This is called Pascal's triangle. Pascal's triangle. Yeah, you got that, right? And then how these terms are made out of is there is a pattern in that. Now you have the two terms in your binomial, a and b. If you go through the terms along your expansion, powers of a in the terms, they go in a certain order. Look at this. Look at the expansion of a plus b to the power of 5. You start a to the power of 5. Next term, it has a to the power of 4. Next term has a to the power of 3. The power drops by 1. 5, 4, 3, 2, 1, 0. And the power of b increases, starts from nothing. There is no b here. And it appears in this b to the power of 1. Then in the next term, b to the power of 2, b to the power of 3, b to the power of 5, 4, b to the power of 5. A to the powers drop, B to the powers increase. They go like that. The powers, the power number. That's all we noticed to write this. So first thing, when I am trying to get a plus b to the power of 6, then I know there has to be 7 terms. So I left 7 spaces by putting pluses, pluses, pluses. I just have to fill out the terms now. And the coefficients I took from the binomial triangle, the Pascal's triangle, I found these coefficients and I know that these coefficients have to come in front of my terms. 1, 6, 15, 20, 15, 6, and 1, 1, 6. I put those in the terms. And then I filled out the powers of A, decreasing powers, and powers of B, increasing powers. Powers of A started with 6, 5, 4, 3, 2, 1, 0. And powers of B go 0, 1, 2, 3, 4, 5, 6. This is how any power of a binomial, that's how it works. Did you understand, Umasha? You can try doing a plus b to the power of 7. Okay, if you tried, okay, so I will leave that as a little exercise to do. Can you write out a plus b to the power? Now we still didn't write the binomial theorem. This is just a exercise for you to understand it yourselves. You're welcome, Umasha. Try to write a plus b to the power of 7. I'll tell you what you have to expect. There must be 8 terms. Power is 7, then there must be 8 terms, one more than the power. Then you can find the coefficients by filling out the next line, like the next base in the Pascal's triangle. Fill the next row. Those will be the coefficients of your 8 terms. And then you can fill out A and B. So I will leave you with that. And you have 1 week to digest this. And I will present you with the binomial theorem. The binomial theorem puts all these patterns that we noticed today into a theorem and gives you a formula. Okay, so we will learn that next week. You have enough homework from sequences and series. and we'll stop with that. So this is a lot, especially now. I know Umasha is not doing this in school, um, so uh, that's why it's taking a little extra time for you to like to, for it to click, and that is completely fine, Umasha. Okay, don't worry. And for the others like Senitu, because they have already seen this before, it goes into them fairly quicker than normal. Okay, right, you're welcome. So